Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Alex Gurvich and Aaron Geller with us today. Hi, Alex. Hi, Aaron.
Hi.
Hi there.
Cool. And Alex, let's start with you. Where are you located at?
So I'm living in Chicago. You might catch a glimpse of some of the downtown buildings behind me. So at the moment, though, I will be moving very soon.
Very cool. Are you actually in downtown Chicago?
Yeah, I'm in the West Loop.
Ah, okay. I lived in the Loop for a while. Very cool.
Yeah.
Very nice. And do I take it it's now Dr. Alex?
It is, yeah, as of last week.
Congratulations, Dr. Alex.
Thank you.
Very cool. Very cool. And where are you headed off to next?
I am starting a job at NASA Goddard as a senior visualization specialist.
Awesome.
Working with the Science Visualization Studio.
Who put out some pretty good stuff. Very nice. Very nice. And Aaron, where are you located at?
I'm in Evanston in Illinois, right where Northwestern is located. And that's where I am right now in the office. And yeah, happy to be here with you.
Cool. It is April 26, 2023 as we record this. And Aaron, is spring actually in Chicago yet?
Well, by the calendar, I guess it's spring, but this morning it was very cold outside, for me at least. We had like a teaser of spring maybe last weekend or 2 weekends ago. It got me really excited. It was like 80 degrees, and I thought spring is here, and it's not.
Yes. I think it's a decade in Chicagoland. I'm familiar with the late arrival. But then all of a sudden the power switch will get hit, and within a week it'll, be 90 degrees and all.
That's right.
Cool. And Aaron, what do you like to do for research?
So I study in general stars and planets, how they're born, how they change with time. And I focus on star clusters. So I study open clusters. I do that through observations and numerical simulations.
Very cool. And Alex, what do you like to do for research?
Yeah, so my thesis was focused on studying the formation, evolution, and stability of galactic disks using cosmological simulations. And I guess it was also split between developing visualization software. So it's Firefly, which I'm really excited to talk about today, is actually a chapter in my thesis. So it makes a big chunk of my research as well, is actually doing this open source software development, which was really cool to be able to do.
Very nice. And that is going to bring us to this very awesome APJ supplement article. It's open access. People can go get a copy for free. It's open source software, so you can grab it for free too. Firefly, browser-based interactive 3D data visualization tool for millions of data points. And Alex and Aaron, take us away.
Yeah, so maybe I can provide a little bit of context for, why make a 3D data visualization tool for millions of data points, let alone one that works in the browser.
Right.
So, as part of my research, I use these hydrodynamic cosmological simulations, which are particle-based. So you can think of them as being kind of like Excel spreadsheets with something like 30 columns and about 10 million rows. And each row corresponds to a single particle. And each of these columns are things like the X position, the Y position, the metallicity, the temperature of gas particles in the simulation. If you're talking about star particles, that's a whole other, Excel spreadsheet. And then they'll have things like their age in there as well. And so, what you end up with is this very rich data set that is very hard to build intuition over. It's like, it's fine. You can make complex plots that can answer really interesting questions. But, when you're first starting a project or trying to explain something to somebody else who might not have the same context or expertise with the data that you have as the PI of the study, visualize. That's where visualization comes in. Is when you want to try and understand what's in your data set and then explain it to somebody else. And so that's the first layer. of the why. Why the heck do something like this anyway? The second layer is that existing visualization tools are good. You know, I want to emphasize that. And when you're trying to use a tool that exists, so it's like, for example, one that I really like is YT for this kind of data, where you can load cosmological simulation data and make these like beautiful renderings of it. Those renderings are expensive. You know, they're hard to make. The computer has to work a lot to render it. And so if you don't know a priori, like, this is the angle I want to take it from, or these are the filters I want to apply, or like, you know, this is the color map I want to use, that can be a very time-consuming process to fiddle with it and iterate and create something that really conveys the point. And as well, you know, that it's limiting in your ability to explore the data, right? Like, because you're taking it from, you're taking an image from one location with one color map, you know, even if you're fiddling with all these knobs, maybe then you're getting to explore, but still that's an expensive process.
Indeed.
And so that's why, you know, we needed a visualization tool, like we being my research group, needed a visualization tool that we could use to explore our data interactively, but then also use to communicate the point as well. And so it's like the 2-in-1. And so that's where we get to the interactive software and the web-based software. And so the interactive piece lets us explore the data interactively, apply these filters, apply everything, you know, that we need to do so that we can build the intuition. But then the web-based lets us share it in a way that then either members of the public or other people in our collaboration can access the visualization in a way that we've preset it up with the right configuration file, you know, so that the view is just there, without you having to fiddle with it yourself.
Or download 19 libraries and try to link them all together. And
exactly, without any kind of installation process.
Right.
So that's kind of the backstory for Firefly. So I think you know, as we started developing it, it became clear that this is a pretty useful tool, and not just for galaxy formation simulation, but also for other sorts of data. And so if we go down to like figure 1, for example.
Figure 1. We slide down, use cases and key features, and there's lots of the URL all over here. You can go get it for free, people.
Yes.
Fireflyvid.com. Figure 1. Okay.
So if we look at figure 1, for example, is like panels A and B are this fire simulation, hydrodynamic cosmological zoom-in simulation data that I work with. But panels C and D are actually observational data. So C is taken from the SDSS Galaxy Catalog, and the colors are from citizen scientists actually denoting the morphology that participants in Galaxy Zoo have decided that each one of these galaxies has.
Nice.
And then D, figure D, or panel D, is a view from within the Gaia DR3 data set, where we're able to interactively visualize all billion-plus stars in the data set, where you can like fly around and data will automatically pop into view as you approach it, without you having to download anything else or like, you know, select something, while still giving you all the same features of Firefly, like being able to filter, pan, zoom, color, you know, do whatever. So
and one of the
we realized that this was more of a general tool than just for the fire simulations, and so we built it that way very intentionally.
Very nice.
Yeah, and if I can just add one thing here, although, you know, this is published in an astronomy journal and we're both astronomers and we're showing right here astronomical data sets, I also want to point out that this is, as Alex said, a general purpose tool. So if you have any kind of data that has 3 coordinates that you could imagine visualizing. I mean, typically that's spatial, X, Y, and Z, but in principle, it could be anything.
Right.
You can put that into Firefly and visualize it. And one more motivating factor is that a lot of the tools that I know, like Alex and I played around with before writing Firefly, had trouble dealing with very large data sets, and particularly data sets like Gaia. So one of the things that we were trying to push the envelope on with Firefly, and one of the things that I personally am very interested in data visualization and visualization software development, is seeing how many particles we can load and how we can do this in a way that still makes the experience interactive, where you can still rotate it around and manipulate the data in real time.
Very cool. And one of the features of the AAS journals is that we have interactive figures. It's an example of an interactive figure. So we're going to stop here for a second. I'm going to go to the online version of the article, and we're going to play for a few minutes with Firefly Has Gone to Sleep. So here's the interactive visual. We've gone to sleep since I've left. I'm going to start it. And there we go.
So yeah, I guess I can kind of talk you through ways to interact with Firefly. So the first thing, that people might notice when they're opening up Firefly is, you're dropped into a 3-dimensional scene. There will be a little message that pops up briefly in the bottom. If you can click that little arrow in the bottom left corner, it'll bring it back up just momentarily. That'll explain how you can manipulate the scene. That'll automatically hide itself unless you've done as we did now is click the arrow. So if we're done with it, we can click that arrow again and hide that message. But what that's telling you is that you can click and hold to pan around and rotate around the object that is at the center of your focus. You can use the scroll wheel, or if you have a touchpad, like just 2-finger slide to zoom. And you can, I guess, is there anything else that you can do in trackball controls? Am I missing something?
Those are the important ones. You can pan the camera if you right-click and drag, but that's not as useful.
Yes, we don't use that as frequently. But then up in the top left corner, you have your little hamburger. So if you click that guy, and the interface opens, then you get a lot more information about the visualization. So the first thing I think we want to do, why don't we click the General tab?
Okay.
Perfect. And then you want to go to, I think it's probably in Camera.
Okay, let's try Camera.
And then why don't we hit that full screen button?
Full screen. Ooh, okay. What happened
there? I think in the interactive frame, it's not letting us do full screen. That's interesting.
This may not work in the AAS Journals version, but it would work on a version that we have on our GitHub or on our website.
Yeah, or like within a Jupyter notebook or something, it does. Even if it's in an embedded pane, go into full screen mode. Well, we'll survive the way
we will survive on this one. This is all an example, and I'm a new user. I've never used this, so the point is you can really interact with it and move it around.
So why don't you go ahead and hit that back arrow to take us back to the general pane, and then back again to go here, and then let's click the particles pane. So the way that we've structured Firefly is such that you can load different kinds of data into different groups. Group your different particles into particle groups. Wow. And so you've already found our toggle button. So why don't you go ahead and play around? Why don't you toggle each one just so that we can see what that's going to do? So there are the gas particles, which currently are being shown as vectors. And then if you toggle the stars, you'll see the little bright white stuff at the center go away. And then we have high res and low res dark matter in fire simulation example that we're looking at, which is off in the background. Those are those purple or magenta clumps. The low res dark matter is just so far away that you can't see it at the moment. You'd have to really zoom out. But anyway, so then we have a very important feature. Yeah, there you go. You found it. So yeah, even still, we're looking at the high res dark matter. The low res dark matter looks more like a cube.
Cool. Where's that?
Um,
Oh, yeah, sure. Mhm.
but anyway, you found already the arrow that, yeah, maybe let's get rid of the color map for now. We don't need it. So you found the arrow that expands each particle group has additional options in the interface. So if you click that light arrow on the right side,
This one?
not that guy, no,
Oh, here.
right next to the red square.
Yeah.
So that's going to open another like nested version of the interface that gives you specific options that are only going to affect the gas particle group. So right now, you found in the general tab the ability to change just some basic properties. Right now, the blending mode and the depth mode are set based off of the color map that we're using. So exactly, just like in like a Photoshop, you can change the way how the pixels are being blended together. So what a normal mode and depth checking enabled does is it applies a consistent color map to the vector. So with additive blending, what we've done is we've added all of the color values along the line of sight, whereas normal is just taking the one closest to the camera once the depth check is also enabled.
Okay.
So the combination makes sense when you have color mapping enabled. So why don't we go to the color map tab?
Okay, color map tab. Yeah.
So just hit back.
And
And then click color map, and then you can disable color mapping.
okay.
For example, let's toggle that. And now the particle group is red, right? And if that's when you enable and disable color mapping, that is what's going to change those blending modes. So here what you've done is now you're coloring by galactocentric radius, but there's some gas particles that are really far out. So the top of your color map is really high. So why don't you click, yeah, so like 6,000, kiloparsecs. So why don't we go into that box? So there's a slider that has two boxes on either side. So why don't we change the value at the top? Let's just type in a new value.
Okay.
And let's change that to like maybe 300. So let's start there. So, okay, much better. And now we can use the top part of the slider and slide it downward until we can start to see a difference in just our disk, for example. So keep on coming in. Now you should start to see some colors changing for the stuff at larger radius. And now we're just like kind of applying a rainbow, or a viridis. The farther the particles are from the center. So that's what GC radius is, the galactocentric radius. And then you can change galactocentric radius to, I don't know, I think we were coloring by velocity before. So maybe let's try temperature.
Temperatures.
The log of the temperature. Yeah, I don't know. Maybe this is what we were coloring by before. I don't remember. But anyway, my point is that there are different scalar quantities that you can color by. And similarly, if we pop out of this view, let's go back one and go to filters. You can do the same thing here. So maybe let's go to the temperature and let's filter out the hot gas.
Okay.
So let's just lower that that value, either using perfect. And so now we're just I think you want to move your mouse, out of the UI and then into the pane if you want to zoom in, if that's what the scroll is.
Nice.
Yeah, and so now we're just looking at the colder gas, and we can see, oh, look, the colder gas is in the shape of a disk, or whatever. Likewise, if you want to filter out the cold gas and just look at the hot gas, you'll probably find that there's these biconical outflows, but also like a hot halo of gas around it. And what I want to emphasize is, I think you got to hit enter for the top value. So it looks like the bottom value you were good, but then you got to hit 7.
There we go.
There we go. And so so it looks like maybe move that slider at the bottom up to like 10 to the 5, and we will start to cut out some of the ISM.
Right.
And then you can see that that gas is more spherically distributed. I'll get to the vectors in a moment, But the other thing I want to emphasize is that right now we're playing with the temperature, that, like in these dropdowns, these are specific scalar fields that I decided that would go into this example. But that's anybody can, when you're making your own Firefly visualization, you can decide whatever scalar fields make sense for your data. You can pre-compute them, attach them to each particle, and they're automatically going to show up in these different dropdowns.
Okay.
And you can identify which ones you want to be able to color by. Maybe you don't want to color by something because it doesn't make sense to color by it, but maybe it does make sense to filter by it. So, okay, it'll show up in the filter dropdown, but not the color by dropdown. Maybe you want to be able to scale the particle by something, but you don't want to, filter by it or whatever. So all of these dropdowns you can individually populate with your scalar fields. And all of that happens in the Python front end. But sorry, I interrupted. You had a question.
No, so is it necessary to pre-compute everything that is shown? So for example, let's say I'm exploring and I wanted to investigate T cubed over rho as some measure of the radiation entropy. Can I do T cubed over rho live on the fly as I go, or do I have to pre-compute that and load it in?
Yeah, so there's no way for you to take existing scalar fields and then compute a derived field from within Firefly at the moment.
Okay.
But of course, you can do such a thing, pre-computed, attach it to the particles, and then it would show up in Firefly.
Okay, cool. Very cool. I love this. This is great.
And then, yeah, I was gonna go and do the velocity panel last.
Okay.
And so if we want to maybe hit back to get out of the gas drop-down filters and go to gas drop-down velocities.
Yep.
So right now we're plotting velocity vectors. But if we toggle that, they'll go back to being little particles, just like everyone. So there's a little, there you go. So now they're just little spheres that are being colored. But in the same way that you can attach scalar fields to each particle, you can also attach a single vector field that will be coded to be labeled as velocity, no matter what. Because that was the data that we had and that we were playing with. But you can put in, like a magnetic field or something, any kind of field quantity, and then plot it as a quiver plot here. But it's going to say velocity. If this is something that users start to use a lot for things other than velocity, that's when I think we start to build out the framework of let's have a separate dropdown for which scalar field you want, and then how do we want it to be labeled, whatever. As it is now, sorry, you're gonna have to live with it. We only care about the velocities, so that's what it's doing. Very cool. Yeah, there's a couple different little tweaks that you can change, like the vector width and whether there's a gradient, whatever. But I want to play with the animate velocities. Yeah, you found it. So let's uncheck animate velocities just for a second, because I want it to be a little bit of a surprise. Okay. And then for T max, why don't we type in 15, and then let's make sure to hit enter, and then go to DT and type in 0.1.
Okay, this is going to be cool. I can say.
Yeah. Then hit enter, and then let's hit animate velocities.
Oh, very awesome.
And so what's going on here is that we have a velocity vector attached to each particle. And so we can extrapolate along that velocity vector in units of dt up to some t max before then we reset the position. Right. So there's no integration that's happening here. It's just extrapolating linearly along the velocity vector. But we're really excited to think about ways that we can include time interpolation, where you're putting extra copies of your data set in at different snapshots in time. And then rather than just extrapolate between velocities, you can interpolate between positions and velocities to make some really nice curved paths. So then you could have interactive movies that you could fly through or filter and color map and etc.
Very cool.
So, okay, that's a lot of monologuing, but I think I've basically covered almost all of the major basic features. Is there anything that stood out to you, Aaron?
No, you did a great job covering all the basic features. Yeah. I mean, there's a few specialized features, and some of this comes in with the help of the Python front end, but all of these checkboxes and every bit of the user interface can be customized such that they show up or don't show up in the version that you use. In here, in the version that we have, there's also an ability to look at it in stereo. So we have like stereo 3D. So we have, I mean, it won't make much sense to do it on YouTube in this setup, but it enables, you know, Google Cardboard, for instance, or if you have one of those fancy older TVs like I do that can do that can make it in 3D with with polarized glasses, you can view Firefly in 3D, which is pretty awesome.
Very cool.
Yeah, I forgot about the stereo feature. Another feature I forgot about, though I think is worth mentioning, is the column density projection. So right now we're just looking at what is essentially a 3D scatter plot or like a 3D quiver plot. So why don't we turn off the animate velocities? We're going to have to check a couple buttons to get this to work. So let's turn on and let's not plot velocity vectors. So let's uncheck that guy. Then let's go back. And then let's go to the filters and let's bring everything back. So I think we filtered out the cold gas. Let's change the filter back to temperature. And let's bring that back to, like, you know, whatever I had it is like 0.04 or something, you know, whatever the coldest gas was in our simulation. Yeah. So make sure we're hitting enter.
Enter.
And then, okay, so the cold gas is back. Now let's go back to gas drop down. So let's leave the filter guy. Hit back. Yes, perfect. And then let's go to color map and let's disable the color map, because the way that the projection works is we're actually taking like the red channel. And so if we're doing a color map, it's going to look wonky. And then let's disable the stars, the dark matters, and both dark matter. Let's just turn them off. Perfect. Excellent. Great. And then the last thing I want to do is let's double click that 0.25 number next to the red square. All the way up at the top. Yeah, and let's make that 1. Perfect. And let's move that slider all the way up to the top. So this is a safety measure. So what we're going to do is we're going to increase the particle size. So now they're overlapping, but this is no good. I can't see anything. So let's go all the way up at the top. It says main particles. Let's hit the back button there. And let's go into general.
Yes.
And then let's go into projection.
Yes.
And let's enable the column density projection.
Ooh, nice.
So let's hide the color map just because it's in the way at the moment.
Yeah.
And so now what's happening is we're just doing a live 2D histogram of particles overlapping each other. Let's maybe take the log 10 of it, because right now the bounds are just like up to like 1 to 10. But now the bounds don't make any sense because we're doing like what is essentially a surface density projection. So let's change the bottom limit of the bounds to like -1. Perfect. And then the top limit, I think I usually like either 0.5 or 1 for this demo. And this is going to depend on like what the point density of your data set is. And so anyway, so now we're looking at column density projection of our data, doing like a live 2D histogram of it, which is more than just, you know, oh, it's like a scatter plot or whatever. One thing that we're really excited about doing sometime in the future is, you know, at the moment, we're just projecting a single quantity and then making one 2D histogram. But we have 3 color channels that we could project at the same time. And so if we could project 3 quantities at the same time, you could do what's like frequently done in like the observations is you're overlaying different layers of the data and like with like false color type stuff. And then we could make some kind of false color image using these 3 different data channels. And in particular, one visualization that I have a lot of experience making with a different visualization software that I developed that is not interactive is making mock Hubble images with simulated starlight. And so I would really love the ability to create something like that live using these sorts of projection. Like these 3 color projections simultaneously. So yeah, I honestly, you know, I think that does the best, you know, example of explaining Firefly. So at that, I think.
And if I wanted, output, like I wanted to take one of these and I wanted to publish it in a AAS Journal article, or I wanted to make a movie to show during a talk or something, can I get high quality output?
Good question. So why don't you hit back?
Okay.
From main general, and let's go to main general capture.
Capture.
And so the output that we have at the moment is that if you really like your image, you can take a snapshot of it. And then you can change the dimensions of that image to like suit whatever resolution you would like. And it's going to render straight to a texture of that resolution. You could also record. I think it's hopefully it's allowing you.
Yeah, well, I will allow, but it's telling me. So it's coming Amazon. Good. Okay.
Perfect. And that should be a little image of what you had. But you can also record a video of yourself in the form of a GIF where it'll let you pan around and zoom and whatever interaction that you're having with the application. It's not going to have the user interface in it. It's just going to have the application.
Yeah.
So I've been using that for talks, for example, to like record myself doing stuff inside talks.
Cool.
So there's that level of output, but if what you want to do is create your own interactive scene, that's where you're going to have to get a copy of the code. We're on PyPy, so you can just pip install Firefly, and that'll work, or you can go to our GitHub and build it from source. Right.
Very cool. Very, very cool. Okay. Well, I want to thank you for that Firefly User 101 tutorial.
Yes.
that was very good. For anybody curious, that was the first time I ever used it. So yeah, it worked well. So let's go back to the article. So we got
So that was figure one. Those are the different sorts of data that you can use Firefly for, that we use, some astronomical data. Aaron, I think, had a great idea with this section where we highlighted some of those features that we just walked through, but like putting it into different contexts, like which ones would be useful if like what you wanted to do was public outreach versus like which ones you would want to use for like, self-exploration. And Aaron, I did kind of want to pass the baton here for a little bit. If you could maybe talk a little bit about the Flask situation and why that would be useful for public outreach.
Okay.
For example.
Yeah, great. So without getting too technical, we have a few different ways that you can run Firefly. And one is with kind of a simple Python server that that is probably the way that a lot of people will initially interact with it. And another is through Flask, which is a Python library that basically launches a more sophisticated server. And the reason why we decided to make these two different entry points is one, the simple server is easy, anyone can use it. But if you want to do something more in depth, like for instance, in this application for public outreach, we needed something that could handle multiple connections to the same scene.
Right.
And so in this scenario, we have two connections to the same scene where one just shows the particles, just shows the kind of visual element, and the other has the user interface. Right. So you could imagine on a big screen, we've done this at the Adler Planetarium, you have a big screen that has just the visual content that you want to show the audience, and then the presenter is holding a tablet that has the user interface and the ability to, touch and drag to rotate the camera the way that you were doing with the mouse. Right. So all of the interaction that you were doing with the mouse there, you could do, for instance, on a tablet or on your own laptop. Cool. And you don't have to show the audience all that interaction. They just get to see all that fun stuff out there.
See the grooviness, the ice cream, right?
Yes.
Exactly. Yeah, exactly.
Very nice. Very nice.
And we've also been using Flask. So talking a little bit about where this is going, where Firefly is going next, we've also been using Flask to find ways to, in real time, interact with the data that's in Firefly through Python. So a lot of what Alex and I do when we're working with Firefly is we're working in a Jupyter notebook.
Okay, yeah, sure.
And so, we might have the data in a NumPy array, and we can send it directly to Firefly through the Jupyter notebook. Okay. And what we're working on right now is figuring out a useful way to select data within the three-dimensional space. So if you found a really interesting region that you wanted to analyze later in Python, you
Mhm.
could select it and then
Oh.
retrieve it into your
Right.
Jupyter notebook
Yeah.
and then do some further analysis in Python later.
Nice.
And that's a feature that's, coming
Nice.
to Firefly soon.
Okay.
Yeah, I think I have to look at that pull request. Like, I
Very cool.
think that's where we're at right now.
Yeah, I'm gonna come back to this point. Very good. Very good. Cool.
So
Anything?
yeah, I really like section 2 for that, is that it really gives like a narrative way of learning a little bit about the features. So yeah, then what we moved on to talk about in the paper was some of the example data sets that were in figure 1,
Okay.
and the different like scientific you know like all of the things that went into it. So it's like, for example, like yeah, we had the 2 fire ones, the SDSS catalog, and then the Gaia points. And the real important thing, in table 1 is just to like look at the number of particles that we were able to load. And so this is where, we talk about like being able to load millions of particles and interact with them.
What does the 7 times mean and the 10 times mean?
Yeah, so that number is emphasizing that the data set actually had 7 times more data in it, but for the purpose of our visualization, we only used 1/7 of it for the visualization. So for example, look at the low res dark matter. That number is really low. We only have 135,000 points like in that interactive visualization because for the purpose of the image, I didn't really care about the low res dark matter, so I culled it by a factor of 50.
Right.
And so part of the reason that we did this is actually a great segue into some of the performance testing, which, just for the sake of time, I only want to touch briefly on, is that, as we were pushing the limits with the number of particles that we could load, it turns out that the thing that was difficult is the amount of RAM that Chrome will let a tab use.
It's a browser. Yeah.
Yeah. So you can have a super cool gaming computer, with 32 or 64 gigabytes of RAM, or you could be using like a high performance computing node with like hundreds of gigabytes of RAM, but Chrome will not let you use more than like 3-ish gigabytes of RAM before it starts to throw errors and get angry. And so that's our limiting factor at this point. So the rendering is we were finding through our performance tests. So if you don't mind scrolling down to that section, there's a good plot like with an image. Keep going. I think it's probably figure 4.
Yeah, this is what I want to see. Yes.
So that's figure 3. So I think we want figure 4.
3, it's performance. Figure 4.
So yeah, so figure 4 up at the top. We were able to put, how did I do this test? It looks like 10,000 particles at like, 200 pixel diameter. So here I'm just showing like 45 pixels. So doing like tons of blending, just having tons of these huge particles overlapping and still get interactive frame rates. So if you had more realistic particle sizes, like something like it looks like I have 12 pixels, you could get up to 1 million of them overlapping on top of each other before you get to an issue. And so the point I want to make is that you would have to have a really dense data set that for some reason you have like zoomed out on that, like, and you have them all overlapping before Firefly can't render it. So we worked really hard to optimize the rendering aspect and the interactivity, and so it can scale to these really large numbers. The issue is literally how many floats you can hold in RAM.
Alex, this might be a good time to emphasize what we did for the Gaia data set, because I want to make sure we have time to talk about the Octree rendering that we did. And just to motivate it, I'm sure that most or hopefully all of the listeners know about Gaia, but it's a satellite that's mapping many of the stars in our galaxy. It's a huge data set that we have, billions of stars. We have their positions in space. We have their velocities. I use it for research. Lots of people use it for research, but it is very challenging to visualize. And as you saw in that table, and the title, Firefly is meant to visualize millions of particles at any given time interactively. And this really is kind of a limitation that we are at, and as a community in terms of hardware and software. It's very hard to get around that unless you have good ideas about how to how to load the data. And this is something that Alex worked on really hard to make work, with me kind of pushing him to really do it. And he did. He came through and like just blew
Aaron
it out of the
believed in
water.
me when I didn't believe in me.
All right.
I didn't think it could be
Right.
done. I didn't think it
So-
could be done, but Aaron was like, I know, you just keep at it. And I ended up writing this octree rendering scheme, which we describe in some of the appendices, which, just for the sake of time, I don't want to dive too much into, but the point of it is that you're only ever loading the tens of millions of points that your browser will let you that are actually in the scene, actually in the camera view.
Right.
So
Right.
that's happening. Yeah. So there's like so that's not shown here in figure C1. But there's this if we actually go to C2, which again I don't want to spend too much time on, there's this whole the purple half of this diagram is this whole complicated system of deciding whether or not we're going to load some data from disk, or if we're going to discard it and then free up room for additional data. And that's just on the post-op end. In the pre-op end, you have to pre-compute this very complicated octree structure, so that Firefly can interact with it live. And that was a whole other half of the project that I had to kind of code and design a system so that we could create an octree which indexed data in space, like its physical coordinates in space, figure out how to map that to where it lived on disk, so that Firefly could load it.
The upshot is that Alex managed to do this so that you as a user don't have to worry about it. So Alex has made it so that, kind of on the Python side, type a command, make octree, and then load it into Firefly, and it'll work. And so we had great success with loading the Gaia data. This is one of, or maybe the only, like publicly available, easy to access ways that you can look at the whole Gaia DR3 data set. And it's freely available right now on our Firefly server for anybody to look at. Cool. And we have not yet found a data set big enough that Firefly can't handle.
Oh, wait for LSST or Roman or
exactly.
Well, yeah, I mean, give us a three-dimensional data set, and we will throw it into our octree and give it a try.
I hear a challenge coming. I hear it.
But I think that's a good place to leave things for Firefly in the paper.
Very cool. This is really awesome software instrument. Very cool.
So yeah, just to reemphasize, if people want it, they can find it at firefly-viz.com.
Yep.
Or on my website, is I think somewhere listed, either in the abstract, or elsewhere.
There we go.
Etc. So yeah.
Cool. Alex,
I hope people use it.
Yeah. Okay. We'll come to that. So Alex and Aaron, thank you so much for walking us through your very lovely APJ supplement article. And you touched upon it a couple of times. And so let me push on it a little bit on where do you think we go over the next 2-3 years on this project?
Yeah.
So, for example, anyone who does software knows that by the time the article is published, it's already lagging behind where the software actually is. So is there going to be a Firefly 2.0? How would users provide input to modify the software to have it more capabilities and this kind of stuff? So what's your projection? And maybe you've got a blackboard there, Aaron, on your right, but sort of where do we go over the next couple of years with Firefly?
Yeah, I was reminding myself by glancing over. Alex and I spent a nice afternoon kind of mapping out what we wanted to do, what's the most important things to do. and what we want to do immediately, and what's kind of a future larger project. So we mentioned a few of those, one of which is coming soon, is the data selection, being able to select data within your scene, pull it back into Python, and manipulate it later.
Right.
But we have lots of ideas. So we want to improve the support for VR. So, you know, right now you can put it into Google Cardboard and kind of look around, but it would be nice if you could easily move it around,
You
you
can
know,
walk
maybe with a
around,
game
yeah.
controller, walk around, you know, there's lots of opportunities for that. And some of this depends on like what the users want, right? But we have ideas, you know, if people really want to use this in a museum setting, for instance, we could include different markers within a scene and allow you to have a museum visitor like touch that marker and move the camera to that location. So kind of have it move throughout a story that you want to tell and have some information about it within there. Right. We have thought about different ways of rendering. So right now we have a particle view, kind of like a 3D scatter plot, but a lot of these cosmological simulations are grid-based, and maybe we want to have volume rendering for the whole thing. So anyway, that's just a taste. And if there are people who have particular interests, you can kind of, well, of course you can send us emails, but you can also submit issues or requests on our GitHub.
Awesome.
That's where all the action is happening, is in the GitHub issues on our GitHub. That's where we keep track of all the milestones that we want, you know, that we think are fun, and that's where like people have been pointing us to the stuff that they're interested in, and also, you know, the bugs that they find.
We can talk about bugs, but anyway, that's all.
It is what it is.
Very cool, very cool. Thank you so much again, Alex, Aaron, and that will do, everyone. And I hope this made your astronomy day, your Firefly day, just a little bit better, and we will see you on the next one. Bye-bye.